measuring a distance in the universe is shockingly difficult. It's far harder than you would ever imagine it was from just like reading like in Scientific American and so forth. And the reason for that is, I don't know, you might have heard of the term redshift. And redshift is often kind of used to kind of say how far away something is, but that actually isn't what redshift is. Redshift is how fast something is moving away from us, not how far away from it is something is from us. If you want to measure how far something away from us is, then you have to be rather careful, because the methods that we have for measuring distances all only work in certain very specific ways. And so what you have to do is you have to use very reliable ways which only work at short distances to work out how less reliable ways work which let you go to bigger distances, and then use those less reliable ways that work at bigger distances to calibrate even less reliable ways which may work at enormous distances. And the overall method is called the cosmological distance ladder, where you use the well understood thing to understand the slightly less well understood but much bigger range method, which you then use again to understand the largest range methods. To run through it at short distances, by short, this is astronomy, right? So short means within our galaxy, which is still a hell of a long way.
Right.
The method that's used is called parallax, and parallax is kind of like this, in some senses, the easiest to understand. The way that a parallax distance works can actually be understood by doing an experiment just like literally in your backyard or wherever you can like see a long way. And that is that if you look at something that's like a moderate distance away, like a tree or like a mountaintop or a building or something, and you look at that building and then you say to yourself, okay, that's cool, but what do I see behind it? And that what you might see behind the tree is like a mountain or a forest, or you might see a building and then behind it you might see a whole bunch of other buildings. But what you then do, if you want to measure the distance to that building or that tree, is you go from your starting point and then you move over some distance, not towards the object, but you kind of move in a straight line that's like parallel to it. And then what you do is you look at what's behind it. And if that object is relatively close to you, then what you'll see behind it will change, because you're changing the direction that you're looking at it. So, for example, I'm trying to think of an example of this. Like, let's say you're at a cross street and you look across the street and you see the light. So you see a red light and you look behind that red light, you might see the street going away, away ahead of you. But if you like cross the road perpendicular to that light and then look at that light again, behind that light, you're going to see a building. And so what you can do is you can calculate, how far you moved. And then by looking at what's behind the object as you move, you can calculate the angle at the top of the triangle that forms, your starting point, your ending point, and where the object you're looking at is. And you can take those two measurements, the distance you move and that angle, and you can use trigonometry to work out how far away that object is. That, as I said, is called parallax distances, and they're the most reliable method we have. And the way that you do those to do distances in astronomy is you say in, January, you observe from the Earth the object that you want to measure the distance to. And then what you do is you wait 6 months and you wait for the Earth to go halfway around its orbit so that it's now on the other side of the sun. And then you look at that same object and you see what's behind it now. And you use that set of information to calculate the angle through which it's moved on the sky. You know the distance the Earth has traveled because it's like half an orbit. And you can use those two measurements to calculate a distance. Those distances work pretty well. The next rung in the ladder are what are called luminosity distances. And the way these work is a little different. The way this works is nothing to do with parallax. What you do, I'll give you the synopsis of it and then I'll give you an example. Mm-hmm. What you do is you find yourself an object far away in the universe and you measure how bright it appears to be. And then you measure some property of that object which tells you how bright it actually is. And then you take those two numbers, how bright it actually is and how bright it appears to be, and the ratio of those gives you an estimate of how far away it really actually is. So I'll give you an example because this one's kind of a weird one. Let's say you're looking out of a window in your house, and you look way down the street, and you know it's nighttime, and you look in the window of another house, and in the room that you're looking into, there's a light bulb on the ceiling. So, this sounds kind of weird, but bear with me. So let's say you get yourself a pair of binoculars and you look down the street and you look into someone else's house and you look at a light bulb in their house. And the first thing you do is you measure how bright that light bulb looks to you. And it's a long way away, so it's going to be kind of dim. But what you then do is you zoom right in on that light bulb until you can read the letters on it. And the letters on light bulbs tell you how bright it actually is. They'll say things like 60 watt or 100 watt bulbs, that sort of thing. Right. So you zoom in until you can read that. And then what you've got are two bits of information. You've got how bright it looks to you from your position way down the street. And then you've got a measurement of how bright it actually is by looking at the letters on the bulb. And you can use the ratio of those two numbers to work out how far away that bulb is, because the further away you are, the dimmer it's going to look. It sounds crazy in some ways, but it's exactly that method that astronomers use.
Like the math works.
Oh, sorry, is the question?
I was just saying the math works.
Oh yeah, absolutely. And I mean, there's some subtleties to it, but the math works really, really well. And so there's two primary types of objects in the universe you can do this with. The first is a special, or not special, a kind of an unusual kind of star. And that star is called a Cepheid variable. And a Cepheid variable is a star that pulsates. It gets bigger and smaller. And when it gets bigger, it gets dimmer. And when it gets smaller, it gets brighter. And astronomers discovered probably 50, 60 years ago that there's a relationship between how bright the Cepheid is and how it pulsates. So what you can do is you can go to a telescope and you can measure the frequency at which it brightens and dims and brightens and dims. You measure how quickly that happens. And then there's a relationship that you can use to calculate how bright it is from that frequency. That works up to distances of the nearest galaxies. But to get really far out into the universe, you need a much, much brighter object than that. And for that, astronomers use supernovae. And in particular, they use a type of supernova called a type 1a supernovae. And it would take a while to get into what that is, but the basic idea is you have a big star and you've got a little star called a white dwarf orbiting with that big star, and some material gets drawn off the big star and onto the white dwarf, and eventually enough of that happens that the white dwarf explodes. And you can see those supernovae to huge distances, like halfway across the universe and beyond. And there is a relationship between the way in which the light from one of those supernovae dims. So they start off, they really quickly get very, very bright. And then over the course of days or weeks, they dim. They get slowly dimmer from their maximum brightness. And there's a relationship between how fast they dim and how bright they are at their maximum. So if they dim really quickly, then they weren't very bright to begin with. But if they dim quite slowly, it takes them weeks to months to get dimmer, that means that at their peak, they were really bright. And so what you can do is you can measure how long it takes that supernovae to get dimmer and dimmer and dimmer over the course of days and weeks. That then tells you how bright it really was. Then you can, again, take the same data and say, well, how bright did it appear to be? And the ratio of those numbers gives you a distance. That's probably the best, or not the best, the distance indicator that goes the furthest. But it's critically dependent on being calibrated on things like parallax distances. They all kind of go together in a chain.
Right.
If you use all of those methods together, then the distance to the edge of the observable universe is something like 90 billion light years, give or take a few billion light years, but it's about 90 billion.
Okay.
You know what's one of the interesting things we always say in one of our famous phrases is that in science you can't skip steps, right? So we had to master those steps in terms of the parallax and being able to measure the distance from the Earth to the sun first, and then he sort of mentioned the whole idea of measuring the luminosity and then measuring the distant galaxies, and then building on all of that information we have, and then now we can measure the distances to the very farthest things inside of the cosmos, which again, right, it sort of backs up that whole idea. You can't skip steps, right?
Oh yeah, that's an absolutely brilliant analogy. It's perfect. I mean, there's so much in many popular science articles, they kind of portray scientific progress as being this big giant leap where scientists just magically do this big experiment and it all works. And the reality is never like that. The reality is it's always this slow, careful, methodical progress. And the distances in astronomy are a perfect example of that. We spent decades working out how to do parallax, then decades working out how to do Cepheids, then a decade or two working out how to use supernovae. It took a long time. So yeah, that's a perfect analogy.
Yeah, Brendan, we always say that those ancient cultures, we do them a disservice when we try to make them skip the steps and know everything that we know. That's, we talk about that. That's very, very disrespectful to those ancient cultures that did what they could do to kind of move humanity forward. Yep, I appreciate that answer right there.
Oh yeah, you're totally right. I mean, I don't know much about this, but I try to read about what cultures across history achieved, and I'm always just astounded by what they did. They did what they needed to do to kind of survive and be sort of peaceful and prosperous. And, compared to today, they might not have done as much as modern civilizations had. But what they did was incredible, and they didn't skip steps. They were methodical, they were careful, they were and so much of modern science is based on what they did.
Well, you just hit a home run.
Yeah, that was excellent.